In this module, we will be talking about derivatives in one variable, some examples, and some basic handy rules in order to calculate this. So if you recall, in the last module, we introduced the notion of a derivative, which was denoted as df by dx, or f prime of x, and was rigorously defined as the limiting value of f of x plus delta x minus f of x divided by delta x as delta x tends to 0. So what this means is that if we have any generic function which looks something like this, we can fix 2 points, one over here at x, one over here at x plus delta x, calculate the difference in function over here. So this one is f of x plus delta x, while this one is, so this is f of x plus delta x, while this is f of x. So we calculate this difference, and that goes in the numerator, and we calculate this difference, and that goes in the denominator. So that's our definition of the derivative. And now let's see how do we actually do it in practice, and what does it look like for many common functions. We are not going to do it for all functions. I'm going to give you a handy summary of what the derivative looks like for function. You can do it by first principles, which actually involves taking this limit for each of those functions. And if we have some exercise problems where you will do that, you can practice that. But in general, it helps to remember these things. I know it sucks that in math you have to go and commit things to memory, but often it is useful. And as you use them in practical examples, many of these will just become ingrained in your memory. So let's look at a few practical examples. So the first example that we will look at is for a function given by f of x is equal to cx. And we want to calculate, sorry, by cx, I mean c multiplied by x, where c is some constant. So c could be 1, 2, 500, minus 18, pi, whatever you want, it's some constant. So how do we calculate f prime of x for this one? So f prime of x at any value of x will be given by, again, limit of delta x tends to 0, f of x plus delta x. So what is that going to be? C of x plus delta x minus f of x. What is f of x? That is c of x divided by delta x. This is limit as delta x tends to 0, cx plus c delta x minus cx by delta x. The cx and cx cancel out. You are left with limit delta x tends to 0. You can also cancel out the delta x from the numerator and denominator, c. And that is independent of whether delta x tends to 0 or does whatever. This is simply c. So we see the example of our first and simplest derivative, that f prime of x for this function is c. Let's look at an even simpler example. Let's look at the example where f of x is not f of x equal to c multiplied by x, but let's look at the case where f of x is a constant is equal to c. In this case, it's easy to show that f prime of x will be limit delta x tends to 0 of c plus c minus c divided by delta x. The numerator here is identically 0, so this thing is 0. However, I must point out here that we will revisit examples like this later in the context of what is called the L'Hopital's rule. But for now, the numerator is 0, so this thing is always 0 for any finite x. If any finite delta x. So the derivative of a constant function is 0, and you can see why this makes intuitive sense. So what are we talking about here? We're talking about a function. Let's look at the, so if you have a function f of x is equal to cx, which we had in the last example, then that's going to look like this, right? F of x is equal to cx. We could also have and in this case, we have a function that looks like f of x equal to c. So the change in this red one is the ratio of the y value divided by the x value is constant irrespective of where you do it. You could do it here, you could do it here, it is constant. This change is simply this height divided by the space. In the black one, again the change is constant, but furthermore the change is zero. You could go from this x to this x plus delta x and there is no change in the function. And that's what reflects that the derivative of this function is zero. So these are two examples where you saw by using the actual formula for the derivative what the value of the derivative is. For the further examples, I'm going to just write down the expression. I'm not going to derive all of it. I will give these in the associated exercise problems along with solutions so you can work through it and see what it looks like. So in this one, our f of x is equal to x to the power n. So f prime of x is n x to the power n minus 1. You can see why the first case that we looked at, if n is equal to 1, then f prime of x is equal to 1. This satisfies the property we did for the first example, right? Where f of x is equal to cx. It is related to that one. But so it's a generalization of that one. And you can also think of what happens, well, instead of f of x, if I had c multiplied by x to the power n, then f prime of x would be n c x to the power n minus 1. For the fifth one, it's a bit generic. Let's look at the derivative of the sum of two functions. The derivative of the sum of two functions is, and you can prove this formula rigorously by using the limit formula that we introduced for the derivative. This is f prime of x plus g prime of x. It's adding the two derivatives together. Let's move on to, so this was number 5. Let's move to number 6, which is a bit more interesting. F of x is equal to sine of ax. Here, you have to use, one way to do it is to use the power series for sine of ax. Sine of x has an associated formula. So this will be one of the homework problems where you will do it. But the f prime of x here, as you will find in the homework, turns out to be, not homework, let's call it an exercise problem. It turns out to be a cosine of ax. So sine goes to cos and the a comes up front. And if f of x was cos of ax, then something interesting happens. F prime of x becomes minus a sine of ax. These two are very useful and often easy to forget that one of them does not have a minus sign, but the other one does have a minus sign. Eighth one is related to the puzzle I left at the end of the last module, where f of x is equal to e to the power ax. In this case, f prime of x is a e to the power ax. As a corollary to this one, if f of x is equal to e to the power x, then f prime of x equal to f double prime of x equal to any order of derivative f100 of x is the same, e to the power x. For this one, however, f double prime of x would have been a square e to the power ax, right? The constant would be treated as it is, and this would give a second constant coming about. So these derivatives, if you have seen them before, these modules should be easy for you, but if you haven't, that is not much complicated. It's important, however, is that you write them down many times, you practice them to do it by first principles by using the limit formula, and then you will not find them to be very difficult. The next one is the derivative of the product of two functions. This is very useful and very interesting, and it looks like d by dx of f of x multiplied by g of x is, you hold the first function constant and differentiate the second one with respect to x. Then you hold the second function constant and differentiate the first function with respect to s. So this rule is very important. It's called the product rule of derivatives. And so a common mistake here that students tend to do is to say that d by dx of fg is df by dx multiplied by dg by dx. This, as you can see, is wrong. So don't make this mistake. You will lose points in whatever course you are taking or make a mistake. If you design an aeroplane based on this formula, the airplane will probably crash. It's a bad idea to use this one. This is the correct formula, where you hold one function constant and differentiate the other one. And I will post some uh, online material going into the details of why this rule is actually valid. Where does it come from? For now, I'm going to skip it. Let's go to another one, which is instead of a product of two functions, what happens if we have a composition of two functions? If we have f of g of x, this one is actually easier to derive. You can think of it as d of f of g of x by d of x is given by d of f of g of x, and think of g of x as a variable on its own. So write it down as d of g of x here and multiply, divide by the same thing, and write a d of g of x in the numerator here. So this thing is written as df by dg, while this thing is dg by dx. So all we have done is to introduce the dg in the numerator and the denominator. So let's take an example of this one. Let's consider the function phi of theta. So instead of f, I'm using phi. Instead of theta, instead of x, I'm using theta. So let's define, so this is an example of an example. And let's define phi of theta is equal to 3 cosine square theta minus 1. And let's define g of theta is equal to cosine of theta. So in this case, we can see that phi of g of theta is equal to 3 g of theta whole squared minus 1. So by the way, this rule is so important. It's got a name of its own, just like the last one was called product rule. This one is called the chain rule. Super important. So now you can see that d of phi of g of theta with respect to theta is going to be d phi with respect to g multiplied by dg by d theta, and you can do d phi with respect to g. That will be 6g. So this is a constant. The derivative of this one with respect to g is 0. The derivative of this one with respect to g is going to be 3 multiplied by 2g. So this is 6g of theta multiplied by derivative of cosine theta. That will become minus sine theta, as we just saw. And g of theta itself, we know it's cos theta. So this thing is minus 6 sine theta cos theta. So this is an example of the chain rule in practice. And the chain rule is super important in physical chemistry. We'll be using it multiple times. We are almost done with the list of the most useful derivatives. Let's look at a couple more. This one is f of x is equal to a to the power x. For this one, our f prime of x happens to be a to the power x log a. And this will be in one of the exercise problems. I will post the solution as to how does this actually happen. It's not very complicated if you use the chain rule. That's the guess here. That's the hint here. And the final one is similar to the product, but now we have a quotient, f of x divided by g of x. How do we differentiate this? The differential for this one is, if this is one of those ones, if you forget, you can directly calculate it by using the formula for the product rule and the chain rule. So d by dx of f by g can be considered as d by dx of f multiplied by g to the power minus 1, right? G comes to the numerator. So now we can use the product rule. So here, if we use the product rule, which was rule number 9 or example number 9, this becomes f outside dg to the power minus 1. And you have seen things g like g to the power minus 1 in the past. This is the inverse of the function. We don't know what exactly it is, but or you can, right now you can just think of it as an algebraic variable without actually having to calculate it. We will get to that in a moment. So f multiplied by dg inverse by dx plus g inverse multiplied by df by dx. So now we can treat this using the chain rule. How do we use the chain rule here? We can say that this thing is f dg inverse by dg, dg by dx, plus g inverse f prime. I'm going to use this shorter notation. Now let's use the rule number, which one is it? It's rule number 3. For x to the power n, we get nx to the power n minus 1. So here, if we use rule number 3, we get f n is equal to minus 1, so we get minus 1. And this thing subtracted one more power, g to the power minus 2, g prime plus g inverse f prime. And now we can write it down that this is f prime divided by g minus f g prime by g square. Here we can multiply a g on the top and make this g squared. So this is 1 over g squared multiplied by f prime g minus fg prime. So as you can see, it looks complicated. And most of the time, this is one of those formulas which I myself don't remember sometimes. It's easy to derive if you remember the rule for the product rule and the chain rule. And in general, if you have the function given, you can just work through the math and see what it looks like. And as a final topic in this module, I want to show you the proof for point number 9, which is product rule, f of f multiplied by g. When we differentiate it, why is it the same as f g prime plus g f prime? It's easy to remember, and you can see intuitively why this is the case. You're holding one variable, one function constant, differentiating the other one, holding the second one constant, differentiating the first one. The proof can be derived by looking at the formula for limit as derivative as a limit, where you define h as a product of f multiplied by g. You are not really required to know this proof for PChem or most of chemistry, but it's useful to work through it once and see what it really means. With that, thank you very much and see you in the next module.